Everyone hold on. Are you dying yet? Like, not yet. And I was like, yeah.
Yeah, it's hard to be a little bit behind. Good morning.
It's still November on the 24th, and we're working towards that. The homework assignment is tomorrow night at 11:59. It's on solutions, the solutions doing in class. The practice in the remediation review and practice packet. That's what you're going to be using in S5 sessions. We have 3 more this week, one today at 4, and tomorrow is 2:30 and 4:30. On Friday, we are going to have an essay writing session. After the essays on the left test, it seems that we need to have a little bit more formal training on it. So our librarian will be here, and you're going to learn to write essays using information that we're going to give you on solutions, which is what we're starting today, aqueous solutions. There is a sign-in sheet going around. At the end of the day today, we're going to take tabulation. If you are one of those people that have 3 absences, which is what you're allowed, or if you have more, you'll get a paper on Friday along with the absence policy to remind you what it says. So we'll look at it. It's on the door. Actually, we have one here. You should all have one, but I think you have one. So the absence policy says in construction, we allow 3 absences. On the next absence, since your final grade will be dropped a total of 10 points for each additional absence. If you're going to petition, you need to petition like I was sick, I was gone, whatever. Within 10 days of the 4th absence, you get 1 absence in chemistry. After that, they turn into zeros. And additional absences will result in a 10-point reduction in your final grade. So don't be absent, because if you are, you lose points. Okay? And we are taking notes to make sure that that's the case. So, we're going to look at the PowerPoint here on aqueous reactions and solution predictive chemistry. We're not getting to solution stoichiometry today. We're just going to look at, we're just going to look at solutions. And the first part, tells us what a solution is. It's a homogeneous mixture of two or more substances. The solvent is the one that's there in the greatest abundance, and the solute is anything else that's in there. So if you have a salt water solution, water is the solvent because it's there in the greatest abundance, and salt is the solute because it's everything else. When a substance, in this case an ionic substance, dissolves in water, what happens is that it's solvated by the water molecule. And salt is the one that is the example that's here. The chlorine or the green spheres and the sodium or the silver spheres that we have there, you can see that the water is coming in and attracting it and pulling the molecules off the surface, and then they surround them, pulls the ions out of the crystal, and then they solvate and surround them with the solvent. This process is called dissociation. So in ionic compounds, they are dissociated. When they do that, and dissociate into ions, we have positive and negative charges in the water, as you can see right here in the picture. A non-electrolyte, something, when ionic substances dissociate, they produce electrolytes. A non-electrolyte may dissolve in water, but it doesn't produce ions. So the classic example is looking at sodium chloride, which is a white powdery substance, salt. It's an ionic compound made of a metal from the left-hand side of the periodic table and a non-metal from the right. When it goes into solution, when it dissociates into ions, sodium ions and chloride ions, it's an electrolyte because of its positive and negative charges. It will support current across that particular solution. A non-electrolyte is one where that doesn't happen. And the other classic example is also a white powdery substance, sugar. Sugar is a molecule that's a molecular compound. It's made up of two elements that come from the right-hand or non-metallic side of the periodic table. It does not dissociate in water. It stays as a molecule. Therefore, it does not support current. So if you plug it into the wall and put two parts of the current that are hooked up to a light into it, it will not light up the light. Sugar will not light up the light, but salt will because it produces ions, positive and negative charges to support current. So we have electrolytes and non-electrolytes. Soluble ionic compounds tend to be electrolytes, and molecular compounds tend to be non-electrolytes except for acids and bases. A strong electrolyte completely dissociates with water, and when the current is passed through the liquid, the light eliminates brightly. A weak electrolyte only partially dissociates in water. And we'll talk a whole lot more about this and do calculations if you're taking Chem 2. But the weak electrolyte will also light up the light, but it won't be bright and shiny. It will be less bright. So, strong electrolytes consist of several classes of compounds. Strong acids, strong bases, and soluble ionic salts. You need to look at this particular chart right here because it's important that you know what's soluble. What do I expect you to know? I expect you to know that all nitrates are soluble. That's what that says. There are no exceptions. Anything that's combined with a nitrate is always going to be soluble. Notice that the next things down on this chart are chlorine, bromine, and iodide. Those are halogens coming from 7 on the periodic table. And they are soluble in everything except when they're combined with silver, lead, and mercury. So if you have sodium chloride, it's soluble in water. But if you have silver chloride, it is not soluble in water. It forms a solid compound and falls to the bottom of the beaker. There are a few things in chemistry you get to memorize. Polyatomic ions, the elements that are made, whose symbols come from something other than English, and solubility. And there's no way to know this other than simply committing these memories. So things that are soluble, everything with a nitrate. All nitrates are soluble. Things that are insoluble consistently, halides, chlorine, fluorine, bromine, iodide, with silver, lead, and mercury are insoluble. Okay? Something else down at the bottom. Notice this is all the way at the bottom. Hydroxides are soluble with sodium and with potassium, but with everything else, they are not. So if you have iron hydroxide, it's not soluble. If you have copper hydroxide, it's not soluble. Sodium and potassium hydroxides are soluble. So, this is what I want you to know. This is where you write this down. All nitrates are soluble. Sodium and potassium hydroxide is soluble. Fluorine, chlorine, bromine, and iodine is soluble with any metal except silver, lead, and mercury. Fluorine, chlorine, bromine, and iodine. Halogens. Fluorine, chlorine, bromine, and iodine are soluble except with silver, lead, and mercury. That's the repertoire for solubility. Strong electrolytes, as said here, all strong acids are strong electrolytes. We looked at them, there were 7 of them, and we talked about the ones that I expected you to know, which would be unique. It's in the naming acid section in atoms, molecules, and ions. It tells you that there are 7 strong acids, and I gave you the list I wanted you to know. This way, if you look it up, you'll remember it. It's in the PowerPoint on atoms, molecules, and ions. Strong bases are compounds that are hydroxides of alkali metals and alkali earth metals. Okay? So, if you're looking for a strong electrolyte, it's going to be a strong acid. It's going to be a strong base, or it's going to be soluble ion salt. A strong acid is one that completely dissociates in water. So when you put it in water, it completely dissociates into its individual ion. A weak acid, which we'll deal with in show 2, is one that sort of dissociates. Some of it comes apart, but some of it still stays in molecular form. The most notable one of those is hydrofluoric acid, HF. It's used to etch glass, but its main claim to fame is that in addition to being a very corrosive acid, it's also a poison. It binds up the calcium and magnesium in your body and prohibits the nerve endings from feeling pain, so that a drop the size of a dime will bind all the calcium and magnesium in your body while it burns through your skin and you don't know it. So all the emergency rooms here in Austin have special hydrofluoric acid protocols because of the amount of microelectronic fabrication facilities that we have here in town. Because hydrofluoric acid can't be treated like just any other acid. And you won't find it supposedly in teaching. So, we're getting to a piece where I wanted to talk to you because this one leads to calculation. We talk about concentrations in solutions, and we do that with a concept called molarity. So 2 solutions can have the same compound in it, but that compound can be in different proportions, so the solutions themselves are different. They're different because they'll have a different amount of moles of solute in the liters of solution. And we're going to do some calculations with that during this video. Molarity is one way to measure the concentration of solutions. As you're going to calculate it, if you have moles of solute divided by the volume of the solution in liters. Now, many times you get the volume of the solution in milliliters, so you have to convert it to liters. And we'll talk about that in a minute. So, molarity is one type of calculation we're going to use. Another type of calculation, well, this talks about mixing a solution. And we're not going to do this in lab, but we're actually going to do a lab on the computer that shows you how to do this without actually getting your hands wet. Another calculation that we're going to do is a dilution. So say you come into the laboratory and you find that you have 10 molar hydrochloric acid. And what you really want is 1 molar hydrochloric acid. How would you go about finding that out? 2 solutions contain that same compound, but they've got it and you want it in a different concentration. Well, the fact that you're going to use is that moles of one solution is equal to moles of another. This is a problem like you do when you make orange juice from concentrate. So you take it out of the freezer, it defrosts, you pour it in a pitcher, and then you add water, and the water makes it so it's drinkable and not eatable. So that's a dilution problem. Now, the formula we're going to use is M1 times V1 is equal to M2 times V2. The reason this works is when you multiply molarity times volume, you get moles. So molarity is equal to moles of solute divided by the volume of solution in liters. So if we take the molarity, whose units are moles per liter, and we multiply it by a volume, whose units are liters, the liters cancel with liters, and we end up with moles. The formula that we have right up there, it allows us to take a concentration of one solution and find out how much water we have to add to it to get to another concentration. We're going to do one of those problems just in a minute. Okay? But things that you need to know. This is the powerful piece of the solution problem. And if you multiply the molarity of a solution times the volume of a solution in liters, it's another way to get to moles. And as we found out in solid stoichiometry, we want to get to moles. Okay? Does anybody have any questions about this stuff so far? Because we're going to do this. Has everybody got the assignment sheet? Anybody missed the assignment sheet? You can come get it. It's up here on the table.
Do you want one?
Okay, so you have in front of you, some problems for calculation. They look like this. And I'm looking for a highlighter. Okay. Two colors in one. Good. Green, I went green. I got green. Actually, you have to come back to me because I see that. Okay, so Mrs. K has noticed. Mrs. K has noticed. Can you turn the lights down? Here we go. That, and I noticed too that part of the problem with solving problems is you know how to solve this type of problem, and you know how to solve this type of problem, but you're finding what kind of problem it is in the first place. It's what makes it harder to do. So we're going to go through these problems, starting with problem number 1, and we're going to look at what we're told in the problem and where it goes in our solution. Okay? So this particular one says, can you see it, or do I need to make it bigger? Volume of milliliters. There we go. Okay, this problem says, what is the concentration of CH3OH, which is methanol, by the way, in a solution prepared by dissolving 11.7 grams of methanol in sufficient water to get 230 milliliters of solution? So we are going to use the yellow marker and decide what it is that we're trying to find. And the question says, what is the concentration of ethanol? So we are looking for the concentration of ethanol. That's what we're trying to find, okay? And what we're given are two other things. We're given that we have 11 grams of methanol, and we're given that we have 230 milliliters of solution. So what we're given to, so what the question asks for is, what is the concentration of methanol? So we're looking for concentration of methanol, and we're looking for that is, our units are going to be molarity. And what we're beginning with is grams of methanol, CH3OH. Now, we know that molarity is equal to moles of solute divided by volume of solution in liters, okay? We have grams of methanol, so we're going to convert our grams of methanol into moles of methanol. And once we get moles of methanol, then we're going to divide it by the volume that we're given in liters, and that's going to give us our concentration. Okay? So we have grams of methanol right here, which is what we're going to start with. We're given a volume of solution. It's going to go right there. What do you see about our volume of solution? It's in milliliters instead of liters, so we're going to have to fix that. Okay? So here's what we're going to do. The first thing we're going to do is find the molar mass of CH3OH. Let me push it up, push it up. So we have carbon and hydrogen and oxygen. We have 1 mole of carbon. There are 12 grams in 1 mole. So we have 12 grams of the mass coming from carbon. How many hydrogens do we have? 4. We have 4 moles of hydrogen. Each one has a mass of 1 gram, so we have 4 grams coming from hydrogen. And we have 1 mole of oxygen, 16 grams in 1 mole. So we have 16 grams coming from oxygen. When we add all of this, we end up with 32 grams per mole for ethanol, CH3OH. So now we're ready to go back to step 1 up here. We have 11.7 grams of CH3OH. Can you still see it?
No, photo.
Thank you. And we're going to multiply that by something to end up with moles of CH3OH. We know that there are 32 grams in 1 mole of methanol. Grams of methanol cancels grams of methanol. When you do this arithmetic, you end up with 0.366 moles of methanol. Okay, so there's where we are at the end of step number 1, right here. We converted grams of methanol to moles of methanol. What are we going to do next? We do have to convert milliliters to liters. I'm going to do that right here. Do you mind? We have 230 milliliters. We're going to multiply it by something to end up with liters. We know that there are 1,000 milliliters in 1 liter. So milliliters pencils milliliters, and we end up with 0.230 liters. I don't care after now if you don't just convert 230 to 0.230. So now we're going to come down here, we're going to divide this by the volume in liters, 0.230 liters. Our units are then going to be in moles per liter, and the number that we get is 1.59 moles per liter. How many significant figures? Look again. There's 3 in one of them. How many in the other one? 2. So our answer here is 1.6 moles. Okay. Okay. Anybody have any questions? Any directions? We're all happy. Okay, let's try the next problem, which is problem number 2. We're going to take problem number 2, and I want you to look at it by yourself for about a minute to figure out what it is we're calculating, and figure out what it is we're using to do that calculation. The problem looks like this. The problem looks like this. What is the concentration molarity of a sodium chloride solution prepared by dissolving 9.3 grams of sodium chloride in sufficient water to give 350 milliliters of solution? So make a plan. But I just need a plan. Okay, so let's look at what we're given in this problem. The question says, what is the concentration of sodium chloride solution? So the yellow is what we're looking for, concentration of sodium chloride solution. And what we're given in the problem is that we have 9.3 grams of sodium chloride in 350 milliliters of solution. So our plan looks very much like the one we just did. We're looking for concentration, and it's the concentration of sodium chloride, and our units are going to be molarity. And we're going to start with grams of sodium chloride, which we have right here. And we're going to convert that to moles of sodium chloride using the molar mass of sodium chloride. Then we're going to divide this by the volume in liters, which we're going to get from right there. And that will then give us our concentration of sodium chloride. Okay, go for it. Solve the problem. If you have a question or you need help, now's the time to raise your hand. If you have a question or you need help, it's time to raise your hand. Anybody need a question? Okay, take another minute. We're through the problem. If you have questions, raise your hand. Okay, so let's look at what we're given. We're given 9.3 grams of sodium chloride in 350 milliliters of solution. And we're going to divide this by the volume in liters, which we're going to get from right there. And that will then give us our concentration of sodium chloride. Okay, go for it. Solve the problem. Just a little bit about it. No, that's okay. Okay, let's look at how we would solve the problem. The first piece is we're going to look at converting grams to moles. We start with 9.3 grams of sodium chloride. We're going to multiply it by something. We end up with moles of sodium chloride. We know that in 1 mole of sodium chloride there are how many grams? 58. Okay, 58.4 actually. Remember, chlorine is one of those ones that we're going to add the extra, and we end up with 0.159 moles of sodium chloride. Next step, we need the volume in liters. We have 350 milliliters of solution. We want to know how many liters that is. In 1 liter, there are 1,000 milliliters, so we have 0.350 liters. Last step, we're going to take the moles of sodium chloride. We're going to divide it by the volume in liters. We end up with 0.159 moles divided by 0.350 liters. And we end up with 0.455 moles per liter. How many significant figures? 2. So what is that? 0.46 molar. Okay, here comes my question. Are you ready for it? Okay, 0.45 2 significant figures. Okay, 0.44 or 0.45. Okay, the rounding rule says statistically that if you have a 5, you're going to round to the even number. Because if you always round up, your answer is always going to be high. But if you round to the even number each time, then sometimes you'll round up, sometimes you'll round down, and you'll get a statistical balance on your numbers that you have. So in this case, you want to keep this number even, so this one is what you're going to use. In the last one, 0.455, we're going to round it. What are we going to round it to? We're going to round it to 0.46 because we want this number to be even. Okay? Next piece of information. 2.41 is the answer. Choose. What's the answer? A is the answer. Is that identically what you calculated? But it's close, right? If I put E, none of the above, would you choose E? No, because the answer with the rounding is what? 2.38, isn't it? Okay, this is requiring you about a mathematical maturity above your age. We're working on this one. So just because the number you got wasn't exactly on multiple choice, you're going to have to make some decisions based on experience if the answer is actually there. Okay, so I'm going to ask you more of these questions as we go along. You need to think about it. This one rounds to 2.4. This one rounds to what? 4.8. This one rounds to 5.3. This one rounds to 1.2. Consider that and look at it. The answer is obvious, right? Okay. Let us continue along this line. We're going to look at another problem. Actually, we are going to skip number 3 and go to number 4. For those of you who plan at some time, to take some type of standardized test that includes college sciences, this is always there, waiting for you to make a miserable mistake. Okay, this particular problem says, how many moles of potassium ion are present in 343 milliliters of 1.27 molar potassium phosphate? Notice how nice. You've got the formula for potassium phosphate. So what you're looking for is moles of potassium ion. And what you're given is a volume of potassium phosphate and a molarity of potassium phosphate. Okay? This is one of those fun and exciting problems because the first thing you're going to do, even though it doesn't look like it, is write a chemical equation. This chemical equation is for the dissociation of potassium phosphate. So it's going to dissociate into potassium ions, and it's going to dissociate into phosphate ions, and we're going to balance it, and what happens? You're going to put a 3 in front of the K, right? So if you have a molarity, if your potassium phosphate molarity is 1 molar, your phosphate molarity is 1 molar. But what's the molarity of your potassium? Well, in this, let's go back and listen to what I'm saying to you. The molarity of potassium phosphate is 1 molar. The molarity of the phosphate ion is then 1 molar. But what is the molarity of the potassium ion? 3 molar, because you have 3 of those for every one of these, right? Okay. The question here says moles of potassium ion. So we're looking for constant. Now, actually, we're going to look for molarity. We're going to look for the concentration of potassium ion, and it's going to be in molarity. Okay? Now, we're going to take the molarity of the potassium phosphate, and we're going to multiply it by the volume in liters of the potassium phosphate, and it's going to give us moles. Actually, this is supposed to be moles, and I messed it up. Will you let me go back? Thank you.
It'll be 10 points off.
Moles of potassium ion.
Yeah, that's point deducted going back.
Okay, I understand. Maybe I can make it up by doing really well in my explanation. Do you think so?
I think so. Maybe.
Okay, so we have moles of potassium phosphate, and then we're going to use our balanced chemical equation to get moles of potassium ion. Okay? Alrighty, so we have 1.27 moles per liter. That's our molarity, and we're going to multiply it by the volume in liters. How many liters of potassium phosphate do we have? 0.343 liters of potassium phosphate, and that's going to give us 0.0436 moles, right? Okay, so that's how many moles of potassium phosphate we have, okay? K3PO4. So if we have 0.436 moles
of K3PO4, how many moles of K do we have? We have moles of potassium ions in the answer, then we want moles of potassium ion in the numerator, and moles of potassium phosphate, can you see it?
Yes.
In the denominator. What number is in front of potassium phosphate? What number is in front of potassium ion? 3. And when we do our multiplication, we get 1.31 moles of potassium ion. Okay? Guess what? This is one of the answer choices. Always. As we this one. Because you got the first step, but you didn't get the second step. I will tell you, on a typical test, I put this problem in, and 75% of the people take the first choice. That's the first choice. Make a liar out of it this time, okay? You go ahead on to the next step. It will be a wonderful thing. And I will be so pleased. Anybody have any questions about this? Why it works that way? Okay. Then let me, that's it, that's all there is to it. Okay, we're going to do one more problem. This is problem number 6. Problem number 6. It says, calculate the concentration of sodium ion in a solution made by diluting 15 milliliters of 0.84 molar solution of sodium sulfide to a total of 250 milliliters. Okay, it's got a bunch of steps here. Are you ready for it? Okay, so we know that sodium sulfide is Na2S, right? Yes. And when it dissociates into sodium ions and sulfide ions, how many sodium ions do we get? 2. Okay, 2. So if the molarity of sodium sulfide happened to be 1, what would be the molarity of the sodium ion? 2. Yes, it certainly would. So let's look at what we're given in this particular problem and what we're asked to calculate. First, it says calculate the concentration of sodium ion. Okay? That's what we're looking for. And we're given a volume and a concentration to start out with. And we're told that we're going to dilute this to 250 milliliters. Okay? So we know our formula, M1V1 is equal to M2V2, will help us with this problem because this is a dilution problem. Okay? Once we know what formula we're using, we're going to write down what we know. M1V1 and M2V2. Okay? Our initial molarity is 0.874 molar. And our initial volume is what in liters? It's 0.050 liters. If you don't believe that, do the arithmetic and prove it to yourself. The volume that we're looking for, our total volume here, is 0.250 liters, right? And our molarity is what we're looking for. In this step, does the molarity of the sodium sulfide give us the molarity of the sodium ion? It doesn't. Why? Because it's not the same. The sodium ion is twice as much, right? Okay, so we're going to put this down. M1V1 is equal to M2V2. We are going to practice something called numbers last. Move the symbols around. So it says M2, which is what we're looking for, is equal to, what's it equal to? M1 V1 divided by V2. And all we have to do is put these in here now. So we have 0.874 molar times 0.050 liters divided by 0.250 liters. Our liters in the denominator cases liters in the numerator. What's our unit going to be? Molarity. Okay, and when you do that particular calculation, you end up with 0.175 molar, and that's the molarity of what? Of the sodium sulfide, Na2S. Do we stop right here? No, we have 0.175 molar sodium sulfide. We're going to multiply it by something to end up with molarity of the sodium ion. The molarity of the sodium ion is over the molarity of sodium sulfide. There's a 2 in front of sodium and 1 in front of sodium sulfide, so we end up with 0.350 molar sodium ion. How many significant figures do we need? 3. We need 3. The least is 3. 50 or 0.874. Okay? There's our answer.
So, all the problems we just worked are things that would be on your homework for tomorrow night. Okay? The assignment that you have for tomorrow, for Friday when you come to class, is to know as much as you can about solutions, about electrolytes and non-electrolytes and dissociation, all the vocabulary. Yes,
Are you going to put the PowerPoint on Blackboard?
it's there. This one's not there? Okay. I will put it there. Send me an email when you get your email account and bombard me with it so I will forget it back.
I'll bombard it.
Yes. Are you okay?
Bombard it. Just like that.